Okay, so this question is about halogens, group 7. We know they exist as diatomic molecules of X2. They're non-polar, and therefore the only type of intermolecular force between them are these London forces. So our question is about how do London forces come about, how do they form? So imagine here an X2 molecule. Okay, so I've just drawn the electron charge clouds. At any given moment, the electrons, actually because they're constantly moving, are really unlikely to be totally evenly distributed. So imagine that they're such that there are slightly more electrons on this side of the molecule. At that moment, so we're just taking a snapshot, this side would be delta negative, this side would be slightly delta positive. And that's called an instantaneous dipole. Instantaneous. And it's temporary. Okay, so an instantaneous temporary dipole because it's constantly changing. Now imagine a nearby molecule, because obviously you would never get one molecule just by itself. We've got millions and millions of them. As this X2 molecule approaches, the electrons that are at this side are going to be repelled away from the delta negative part here of this molecule. So our electrons are going to be moved this way, leaving this end of the molecule slightly delta positive, this end of the molecule slightly delta negative. And now you can see you've got an attraction between the delta negative and the delta positive. Okay, and that's what London forces are. So this is an instantaneous dipole, and this is an induced dipole because it's caused by the instantaneous dipole there. So for our marks, we need to say firstly that there's an uneven distribution of electrons in the molecule at a given moment, causing an instantaneous or a temporary dipole. So uneven distribution of electrons causes, so that's the first bit, causes instantaneous dipole. That's the second mark. And then this therefore causes an induced dipole on a neighbouring molecule. And there are your 3 marks. Okay, so second question, we're looking at boiling temperatures. So we're still thinking intermolecular forces, don't get yourself confused. So they're covalent molecules, but we never break bonds in covalent molecules when they boil. We're just overcoming those intermolecular forces. So the strength of the intermolecular force, the strength of the intermolecular forces determines the boiling point here. Okay, so bromine's got a higher boiling point, and we've already ascertained that we've only got London forces between the molecules. And bromine's got the higher boiling point just because it's got more electrons. So first mark, Br2 has more electrons. Be careful, don't say Br, it has to be the whole molecule. Has more electrons than Cl2. Therefore, the London forces are stronger. Okay, and you can see why that would be. Okay, so the London forces are stronger. That means that more energy is required to overcome them and to pull the molecules away from each other. You can see why that would be, because if you go back to our description of how London forces are caused, if you've got more electrons, the size of that instantaneous dipole has the potential to be bigger. You get a more uneven distribution, and so therefore you're going to have a stronger attraction there between your instantaneous and induced dipole. Okay, so a slightly longer question now, looking at an experiment. So read it through, be careful reading it through, make sure you understand what it's asking. Looking at these, this very much reminds me of the GCSE halogen displacement reactions. So you did them at GCSE, you've also done them at A-level. Okay, and that makes sense because you're trying to determine the order of reactivity. Now you know that as you go down the group they get less reactive because obviously the halogens want to gain electrons when they react, and it's easier to gain an electron at the top of the group because there's less shielding at the top of the group, so a greater attraction to the nuclear charge. So here we've got bromine iodine and then our potassium halides. And we haven't got access to chlorine gas, that's okay. And then we've got this organic solvent, cyclohexane, which you should remember from doing this experiment in the lower sixth, dissolves non-polar molecules. Okay, so it's an organic solvent, it's non-polar, and therefore the non-polar halogen molecules are going to dissolve. but the ionic compounds, the potassium halides, are not going to dissolve because they're ionic, they're charged, they will only dissolve in polar solvents. And when bromine dissolves in cyclohexane, you get an orange colour. And when iodine dissolves, you get a funny purpley pink colour. It doesn't matter whether you say pink or purple. Okay. Now we need to carry out the smallest number of experiments possible in order to work out the reactivity. We need to describe what we do, so describe the experiments, and we need to give the observation. So I'm thinking observations on adding cyclohexane, okay, because that's what the question says. And we must have an ionic equation. So first one that I think you would do, the most obvious one, is to mix bromine with KCl. And you know that that reaction wouldn't happen because chlorine is more reactive than bromine. The bromine isn't able to take the place of the chlorine in the KCl. Okay, so there wouldn't be any visible change. When you add cyclohexane, because the bromine is still present, it would go orange. So add cyclohexane, orange colour seen as the bromine dissolves. And the presence of that orange colour would tell you that the bromine reactant hadn't been used, it hadn't formed a new product. Let's think of another experiment you could do. So we could add bromine to potassium iodide. Okay, now this time bromine is higher up the group. We know that therefore the bromine is going to displace the iodine in the potassium iodide. So when this is the reaction that happens, so Br2 plus, we want an ionic equation, so I'm going to leave out the K plus. So Br2 plus I minus goes to, let's balance it up actually as we go, 2Br minus, so that's now in the potassium bromide, plus I2, okay? And the I2 dissolves in the cyclohexane, okay? So we add our cyclohexane, the bromine has been used up, okay, and because we made the iodine, so it dissolves in cyclohexane, giving this pink colour. So we can see that reaction has taken place. Now let's have a think. We've done 2 experiments. Is that enough? So we can tell in our order that Cl chlorine must be more reactive than bromine from the first experiment. We can tell that. So Cl more reactive than Br. Okay. We can tell that from this one, Br is more reactive than I. And so I think we've covered it with just 2 reactions. Okay, so here are our marks. We need, first of all, 1 there for mixing bromine with KCl. Then we get 1 mark for having this one. We get 1 mark for having the colours of the halogens in cyclohexane. So we need both. We need the orange colour there and the pink colour here. So that's 1 mark together. And then we need a correct ionic equation there. So 1 mark. And then the final mark is for only using 2 reactions. So together we get the final mark there. So 1, 2, 3, 4, 5 marks. Okay, so we've got another experimental question. This one's quite long, so it may be worth going through and just highlighting important information as you go through. So we're looking at identifying a group 2 carbonate. Worth knowing it's group 2. We have got the white solid. That's what we'd expect because main group compounds form white coloured compounds, whereas transition metal compounds form a coloured. The label's missing, but we know it's group 2 carbonate. And okay, so it's an anhydrous white solid, it's pure and dry. So that's immediately making me think in any mole calculation, I can use the mass of my white solid and to get the moles of solid. There isn't anything else in there. Then we've got 3 different ways of identifying it. We're told we've got the same balance. I'm guessing because they've said that that's going to be important later on. And okay, we've got the first one is looking at reaction of acid with metal carbonate to produce carbon dioxide, and then we're measuring the volume of carbon dioxide evolved. We've got nitric acid and it's in excess, and I've got apparatus that I very much recognize. So looking at this apparatus, I'd be thinking straight away, okay, it's not the most accurate technique. Sometimes when you put the bung on the top, there's always a bit of a time lag, so gas can escape. So our volume of gas measured is always slightly smaller than it should be. Carbon dioxide dissolves a little bit in water as well. That's another reason why our volume of gas might end up being slightly smaller than it should be. So those would be the things I'm thinking of as I go along. Okay, so we've got the student weighing out some of the carbonate, adding it to the conical flask, adding their nitric acid. We've got the volume and concentration. I'm guessing we maybe need that later, and then putting the bung on the top. And it's done at room temperature and pressure. Now that's my signal that in a mole calculation I can just use moles equals volume over 24,000 or volume over 24 dm cubed. And then all of group 2 carbonate reacts and we get some results. So let's have a look at our results table. Okay, so they've got the weighing bottle and the carbonate, mass of the empty weighing bottle. We need to do a straightforward calculation to work out the mass of carbonate used. So let's get our calculator, do that straight away. So really easy, 13.247 minus 12.431 gives me 0.816. And on these questions, always give the mass to the same number of decimal places as all the other masses that are given. Then part B, calculate the amount in moles of carbon dioxide collected. Okay, so we use our equation, moles equals volume over 24,000, so moles of gas equals volume. Because it's in centimeters cubed, I'm going to divide by 24,000, not 24. So there's my volume of gas collected, 225 over 24,000. Okay, and always show your working, important to show your working. Gives me 9.375 times 10 to the minus 3 moles. Okay, I'm going to keep that number because probably I'm going to use it a bit later. Okay, part C, calculate the molar mass of the group 2 carbonate to an appropriate number of significant figures and then work out the identity of the group 2 metal. Okay, so we want the metal. Okay, if I know that I've got the number of moles of carbon dioxide, I know that I can use the ratios in the equation to get the number of moles of the metal carbonate. So let's set up our equation. The metal carbonate, since it's group 2, must be just MCO3. There's only going to be one metal atom to one CO3 2 minus ion. Because group 2, it must be a 2 plus ion, so you just need one to balance the charge and make it neutral. We were told it was with nitric acid, reaction with nitric acid. So we're going to form MnO3 2. You actually don't need to go this far, but it's worth just thinking through why it's this. So nitrate NO3 minus, so we're therefore going to need 2 nitrates to balance the M2 plus water plus carbon dioxide. Balance it up, so we need 2 lots of that, and then I think we're okay. Important thing, 1-to-1 ratio of the metal carbonate to the carbon dioxide. So therefore, the moles of MCO3 equals moles of CO2, which we've already calculated, and that's 9.375 times 10 to the minus 3. Okay, in the table, I was given the mass of metal carbonate that I used. So it was 0.816. And I've got an equation that links moles to mass. So moles equals mass over MR. I've got the mass and the moles. I'm trying to find out the MR. So MR equals mass over moles, which equals 0.816 from before, divided by 9.375 times 10 to the minus 3. Okay, so I'm going to put that through my calculator. 0.816 divided by 9.375 times 10 to the minus 3 gives me 87.04. And I think 1 decimal place makes sense for a relative formula mass. That's what you get at A level for your relative atomic masses in the periodic table, so 1 decimal place makes sense. Now, I haven't done enough yet. I've got the molar mass of the whole substance, the MCO3, and I need to find the identity of the group 2 metal. So that 87 is going to be the whole thing. So MR equals 87.0. So if I subtract the carbonate bit, the CO3 bit, I will end up with the AR of M. So AR of M equals 87 minus the carbonate bit, which is 12.0 plus 3 times 16.0. Put it through your calculator and we will get an AR value. So 87 minus 12 and then minus 48, so that's 3 times 16, gives me 27. Okay, at which point, again, 1 decimal place would be better. And I'm going to look at my periodic table, and 27 matches up most closely to magnesium. So it's too far away from beryllium or calcium to be those. So I'm going to say, therefore, M is magnesium. I think that's okay as an answer. It's not 24.3, which is magnesium's relative atomic mass, but it's an experimental result, so I'm expecting there to be a little bit of error in there. So let's just go through marks and work out what you get marks for in that question. So firstly, your moles of MCO3 there. Your method for calculating the molar mass of MCO3, so that's this stage here. Then your molar mass final answer to 1, 2 or 3 SF, so that's their identification of group 2 metal by the name or the formula, which is what we've done here, and so we've got our final answer. Okay, so we've got a repeat of the same experiment by student 2, but somehow student 2 gets a higher molar mass for the metal carbonate, and we need a procedural error which could have made the molar mass greater. So let's have a think about this. We've already said that the main error in this experiment is not replacing the bung on the conical flask quick enough, and that would result in having a smaller volume of gas produced over here. So if we go back to our calculations and kind of track it through and see how that would affect our results, if our value here is a smaller one, we will end up with a smaller number of moles of carbon dioxide here. Okay, so going back through our longer calculation, that would mean that we'd have a smaller number of moles of metal carbonate. So because it's on the denominator there, we'd be dividing by a smaller number, which means that our answer here would be larger. So we would get a larger molar mass. Okay, so the answer must be that student 2 didn't replace the bung quickly enough. So student 2 did not replace the bung quickly enough. And just worth explaining why that affects the result. It means that some of the carbon dioxide escaped rather than going into the measuring cylinder. So did not replace the bung quickly enough. So CO2 escaped. Okay, and so 2 marks for this question. 1 is for identifying, 1 is for saying that the carbon dioxide escaped. Okay, so it was later discovered student 2 had used 110 centimetre cubed of the acid instead of 100, so he used more than he should have. Why wouldn't this mistake have affected the student 2's results? Well, the clue was back in the question, and we highlighted it. There was an excess of nitric acid, so if it's not the limiting factor and you add more of it, it's going to have no effect on the number of moles of carbon dioxide made. Okay, so straightforward answer. The acid was in excess. Teacher noticed that student 2 had used the group 2 carbonate in powdered form rather than lumps. Explain how this would affect the rate and the final volume of gas. So we need to put in 2 things. And explain means we're not just stating whether it would increase, decrease or not affect. So rate of reaction, powder, you know, has a larger surface area, so the rate of reaction would increase. Okay, so rate of reaction increases because of larger surface area, and that means more frequent collisions between the acid and the particles in the metal carbonate, larger surface area. So that's going to be 1 mark. Second mark, final volume of gas produced. Well, there's the same number of moles of metal carbonate in the first place, therefore you have to make the same number of moles of carbon dioxide, and therefore the final volume of carbon dioxide will be the same. So volume unchanged, because there is still the same number of moles. There is same number of moles, or same mass, doesn't really matter which you say, of metal carbonate present. Okay, so even though it's more finely divided, it's still the same number of moles. 1 mark for each. Okay, so student 3 doing a slightly different experiment. They're doing a thermal decomposition and measuring the mass of the reactant and the mass of the solid product afterwards. So we know that when you heat a metal carbonate, group 2 metal carbonate, you form the metal oxide. So let's start off by writing the equation. So MCO3, we've already talked through why it's that formula, is going to form the metal oxide again. So oxide O2 minus, so only one M, one O, plus carbon dioxide. Okay, and it does say including state symbols. So think about it. These are both ionic compounds, metal plus non-metal, so they're going to be solids because they've got high melting points. And carbon dioxide, you know, is gas. Okay, and we need to work out the molar mass of the group 2 carbonate. So first job is going to be to work out actual masses of the substances that we use. So we've got the metal carbonate, we've got the carbon dioxide. Let's look at the mass of carbon dioxide is going to be the difference at the start compared to the end. So mass of CO2 equals 20.447 minus 20.205. It's always worth showing your working, even though this is quite a straightforward calculation, just so that the examiner's got it there and can give you method marks if you need them. So 20.205 and we get 0.242 grams. Okay, and I know straight away I can get therefore the number of moles of carbon dioxide from that. Let's think about what else I'm going to need. Let's do the mass of metal carbonate. Okay, because that's what I'm trying to find the molar mass of. So think about it. If I can get the moles of carbon dioxide, I can use the ratio in the equation 1:1 to get the moles of metal carbonate. And if I've got the mass of metal carbonate, I can rearrange my equation like I did before to get the MR. The metal oxide is not really relevant because I'm not trying to find out anything about it. So I'm just going to use these two. So mass of metal carbonate is going to be 20.447 minus 19.996. Okay, and again, just stick it through your calculator. 20.447 minus 19.996 gives me 0.451 grams. Okay, so now let's get the moles of CO2. So I've got the mass. So moles equals mass over MR, 0.242 divided by 44.0, so just 1 carbon, 12 plus 2 times 16, so 0.242 divided by 44, 5.5 times 10 to the minus 3. Okay, therefore moles, because it's a 1:1 ratio, moles of metal carbonate is the same. And now I'm doing the same method as I did just over the page before. MR equals mass over moles, little rearrangement. Mass I've just calculated as 0.451 divided by the moles, 5.5 times 10 to the minus 3. And let's see what we get. 0.451 divided by 5.5 times 10 to the minus 3. 82. Okay, and that makes sense. It's similar to the answers that I've had previously. You should always think, does my answer make sense? And let's just go through where the marks are. So the first mark is for doing both these masses. Doesn't matter if you got the metal oxide as well, it's not really relevant, so we'd ignore it. Calculation of moles of carbon dioxide, we've got that there, and calculation therefore of the molar mass. So 3 marks. Okay, so student 3 doing the thermal decomposition used the same balance as student 1. Give a reason why the mass of carbonate measured by student 3 has a greater percentage uncertainty than for student 1. So you know, or you should know, the percentage uncertainty depends on the measuring instrument. So it depends on the uncertainty of the measuring instrument. So that could be plus or minus 0.1 grams. You're not told what it is in this particular case. So it's the uncertainty divided by the reading or the measurement, and then obviously times 100. Now the uncertainty has to stay the same if they're using the same balance each time. So the change must be the reading. Okay, so let's look at the masses that the two students used. Okay. So the one we just looked at, student 3 had a mass we calculated of metal carbonate of 0.451. Okay, so student 3 used 0.451 grams versus student 1. Let's go back to student 1 information. And our table from before said that student 1 used 0.816 grams of metal carbonate versus student 1 used 0.816 grams. So student 1 had a larger reading here, and a larger denominator here is therefore going to result in a smaller percentage uncertainty. So student 3, smaller reading means larger percentage uncertainty. Okay, so final point I would put is student 3, smaller measurement leads to higher percentage uncertainty. Try not to write in the margins like this. Okay, so student 3 noticed on heating that some solid was lost. Okay, so that would mean that it would look like more carbon dioxide had been produced, more gas had been produced than actually was, and therefore the moles of carbon dioxide would be bigger, and therefore if the moles of carbon dioxide are bigger, let's go back to what we did over here. Moles of carbon dioxide larger, therefore the moles of metal carbonate calculated would have been a larger value. So we're putting a larger value on the denominator there, and so we're therefore going to end up with a smaller MR value. So let's write that out. So the marks are going to be it would seem that more carbon dioxide given off appears more CO2 produced. So therefore moles of CO2 calculated would seem larger. 1-to-1 ratio, so moles of metal carbonate would be bigger, and therefore dividing by a larger value, gives smaller molar mass. And looking at the mark scheme, your marks are for this first bit, and therefore the molar mass is smaller. So you don't have to do all the explanation, but it's worth thinking through in order to get there. Okay, on to question 3, and it looks like a bit more of an organic chemistry. So we're doing a chemistry question. So we're doing oxidation of alcohols. That's one of the core practicals, so you should be really familiar with it. But we're going to start off, because it's synoptic, starting with a redox equation. Let's get some different colour pens here and work out what's going on. Remember, whenever you're doing a redox equation, the first thing that's worth doing is balancing anything that's changing oxidation state. So look at the oxidation states. We've got H plus and H2O. Both of those are +1. Oxygen in all its compounds is -2. Obviously, we know if it's with fluorine, it's slightly different, but here we're -2. So it's the chromium that's changing oxidation state. We've got chromium in +3 oxidation state over here, and you know that it's dichromate 6. You're told it in the question over here, so you don't even have to work it out. 2 lots of chromium here means we're going to need 2 over here straight away. And so we have got 2 times +6 going to 2 times +3, so 12 to 6. So we're talking about 6 electrons being transferred It's reduction because the oxidation state is going down. So it's plus 6 electrons. So we're now in a position where we can fill in our equation. So I've balanced that. I can put in my electrons, and then remember you need to balance up the oxygens and hydrogens. So we've got 7 oxygens in the dichromate 6, so we're going to need 7 waters over there. We've now got 14 hydrogens over here, so I'm going to need 14 H+. And I can do a final check, because always, not only should your atoms balance, but also your charges. So we look at our charges. I've got -2 plus 14, so that's plus 12, -6, so plus 6 over here, and then 2 times plus 3 over here equals plus 6. So my charges balance as well as my atoms. And colours, you should hopefully know, you should remember these. Orange for dichromate 6. H+ ions, well, they're just colourless. Acids, colourless. Chromium 3 ions are green. Again, learn it. And obviously water is colourless. Okay, so we've got our reflux apparatus, which is very familiar to us. And obviously you heat your, if it's a primary alcohol, in your pear-shaped flask, and you do it with reflux in order to get full oxidation to the carboxylic acid. Okay, and question 1, be careful not to miss this. There isn't a space for answering it, so it's very easy to miss it. The Liebig condenser has been set up incorrectly. Add shading to the diagram to show the water in the condenser. Okay, so if it's going in at the top, it's going to just take the shortest route. So it's going to fall down the side and fill up at the bottom, and then fall out through there. So that's the kind of shape we're looking at. Okay, state how the granules prevent bumping. So anti-bumping granules. What they do is they provide a surface, not a surface area, they just provide a surface for bubbles to form on. So provide a surface for bubbles to form on. And what that means is that you get lots of small bubbles produced. Whereas if you don't have the anti-bumping granules, you just get really large bubbles. The bubbles build up and up and up until they're really large, and that's what causes the bumping. So if you provide a surface for the bubbles to form on, you get lots of smaller bubbles, and it prevents the bumping. So that you get the mark just for saying providing a surface for bubbles to form. Okay, and our carboxylic acid produced. So here's our primary alcohol is oxidized to our carboxylic acid. We need to work out which alcohol we have. So there's our alcohol bit. We wouldn't have had the double bond, so it has come from this alcohol. Okay, obviously though that double bond O would there be hydrogens. So we've got 3 carbons in a chain, so it's going to be based on prop. So we can immediately rule out those 2. So it's going to be either B or D. And then we've got our OH group on the first carbon and our methyl group on the second carbon. There's our 3rd carbon there. So we have got 2-methyl propanol. Okay, using the apparatus for distillation instead of reflux, so that would be the condenser the other way around, or just sideways, horizontally rather than vertically, is not an efficient way to produce ethanoic acid from ethanol. I'll explain why. Okay, so if you've got your distillation apparatus, the first stage is that ethanal, the aldehyde, is produced. So ethanol is oxidized to ethanal. Now that's exactly the same in the reflux condenser, so no difference yet. But if you've got the reflux condenser, ethanol's got a low boiling point, and so as soon as it's produced, you're heating, it will rise up the condenser and it will cool down in the condenser and fall back down, which means that it's able to react with the excess oxidizing agent in here. If you don't have the condenser this way round, it will rise up because it's got its low boiling point, and it will just pass straight through the distillation apparatus and you get the ethanal produced. So reflux is always used to prevent volatile substances from escaping, or low boiling point substances from escaping. So ethanol is oxidized to ethanal. Ethanal has a low boiling point or is volatile. And would escape if you had distillation apparatus. Okay, and that's pretty much what the mark scheme says. So we'll go there. So first mark is for saying that, for understanding that the ethanol is oxidized to ethanal. And then second mark is either for saying low boiling point, or it will distill off before the ethanoic acid can be formed, allow more volatile. So you've got both ideas there. Okay, question 4. So hydrolysis of a halogenoalkane. That's a reaction you should be really familiar with. You could do it with water as the nucleophile. You can do it with hydroxide ions as the nucleophile. But the key thing here is we're looking at chiral molecules. And you should know the definition of a chiral molecule. So let's start with that. A chiral molecule is one that has isomers that are non-superimposable on each other. Isomers that are non-superimposable, and the reason they're non-superimposable, or the way it arises, is that there are 4 different groups attached to a central carbon atom. So we'll write that down as well. So isomers that are non-superimposable on each other, because there is a carbon atom attached to 4 different groups. Note that it must be different groups. It's not 4 different atoms or 4 different molecules. Just be careful with your language. So 4 different groups. Okay, and then we need to draw our diagram. And the way to draw 2 enantiomers is to draw them just as mirror images of each other. Okay, so take the carbon in the middle and then draw yourself a tetrahedral arrangement round the edge of the carbon, because obviously the carbon's got to be attached to 4 different groups, and then just draw the mirror image the other side. So there we go, you can see I'm drawing my wedges and my bonds going into the paper as mirror images, and we need to do butanediol. So I'm going to draw myself a quick sketch to work out where the chiral center is and make sure that I'm doing this right. So we've got an OH attached to the second carbon, and that means that's an H. These are H's. Okay, so I can see where my chiral center is going to be. It's on this one. Okay, so we've got 1 hydrogen attached. I'll draw the hydrogen on there. 1 OH group attached. I'll draw that there. 1 C2H5 group attached, and then 1 CH3 group here. And I'm just going to draw the mirror image now on this side. So CH3, H at the top, OH here. Make sure you draw it with the O attached to the carbon, not the hydrogen. Just be careful with that kind of thing. And the same here, the carbon is attached, not the hydrogen. Okay, and we're done. Okay, so we've got a longer question here, 6-mark question. It's one of those ones where there are lots of indicative marking points and you have to put everything together to get your full marks. We need to compare and contrast, so I'm expecting some similarities and some differences, with a focus on the mechanisms of hydrolysis using aqueous potassium hydroxide. So the hydroxide ions are going to be the nucleophile here, and we know, so I've labelled already, the halogen atom in a halogenoalkane is electronegative, so it draws electrons towards itself, making it delta negative and leaving the carbon it's attached to delta positive. So halogenoalkanes are always susceptible to nucleophilic attack. The X- is a good leaving group, so we get nucleophilic substitution reactions. So you could actually write that down straight away as a similarity. So both halogenoalkanes, we've got a primary and a tertiary halogenoalkane. Both halogenoalkanes undergo nucleophilic substitution to form an alcohol. But you'll remember that there's a couple of different mechanisms for this. And the one that happens depends on the structure of your halogenoalkane. So a tertiary halogenoalkane, we could start there. A tertiary halogenoalkane looks like this. 3 R groups. What happens in the first stage is that the CX bond breaks. Okay, and that's a slow step, so rate determining step, to form a planar carbocation. So here's our carbocation. It's actually trigonal planar Okay, now the question says I don't need curly arrows, but I've added them in because you could anyway. This tertiary carbocation can exist because these R groups push electrons towards the positive charge, therefore stabilizing it. It's called the positive inductive effect. So the positive inductive effect stabilizes the carbocation, which means that that first step can happen. If you can't form a relatively stable carbocation, that first stage just can't happen at all. So positive inductive effect stabilizes carbocation. And that means that then the second stage, so OH minus comes in and it's highly attracted to the positive charge. So that second step is really fast. Okay, and in that final stage, we then form our alcohol. Okay, now in this case, all of our R groups are identical. So there's no, sometimes this question can talk about chirality and that kind of thing. If these groups had all three been different, the OH minus at this stage could either have attacked from above the plane, so this is in the plane of the paper, it could have attacked from above, or it could have attacked from underneath. And if the three groups were different, you would then end up with an alcohol with 4 different groups, and you'd get a racemic mixture of the 2 enantiomers, so 50-50 mix of each. This question's not about that though, so we're not going to worry about that for now. So that's called SN1 because there's only one molecule involved in the rate determining step. One species involved in the rate determining step. Okay, now with our primary halogenoalkane, we can't get SN1 because we can't form a stable enough carbocation because there's only one R group. So if I draw it, I'm going to actually draw it in 3D and you'll see why in a minute. So there's my X off the side, there's my R group, and I've got an H and another H. Okay, you can see because there's only one R group, that CX bond is not going to break in the same way as we get here. So what happens instead is the OH minus nucleophile attacks the delta positive carbon atom. And rather than getting an intermediate that we can isolate, a charged intermediate here, we get a transition state, and a transition state just shows the new bond partially formed and the old bond partially broken. So I'll draw the transition state since the question asks me to. We tend to draw them in square brackets. So here's my OH minus that will attack the opposite side of the large X atom, and dotted line shows a partially formed bond. So there's my central carbon, and then I've got a partially broken bond to my X, the other side. And at this kind of instant in time, it's just a snapshot really, I've got effectively it's a trigonal bipyramidal species. Okay, and it's negatively charged because it's picked up the OH minus, so it's neutral to start with. Now it's negative because we've picked up an OH minus. And in the final stage, that bond totally breaks because carbon obviously can't have more than 4 bonds. So as that forms a new bond, the carbon halogen bond has to break. And so here's our final stage. Now, because the OH minus is attacking from this side, there we go, carbon, it pushes all of these this way. There we go, it's kind of almost flipping the molecule. So if you start with only one enantiomer, which we haven't done in this one because this is not a chiral substance at all, a chiral molecule at all. But if we had 4 different groups to start with, we would only have formed one enantiomer at the end, okay, because it has to flip, go via this transition state to make it one enantiomer at the end here. And this is SN2 because there are 2 species involved in the rate determining step. Okay, so there's only one step, so that is the rate determining step. So let's have a look at our indicative marking points and see what we've got. So indicative content, we need that they're both nucleophilic substitutions. So there's one indicative marking point. It says hydrolysis mechanism for the primary alcohol is SN2. So we've said that here, via a transition state, and the mechanism for the tertiary is SN1 via a carbocation intermediate. So we've got that. Our rate determining step for the primary alcohol involves the OH minus and the halogenoalkane. I've got that. And forms a transition state with the correct diagram. So there's my transition state with the diagram. Whereas the tertiary forms a carbocation intermediate, which is there, and I need to draw the diagram and include the charge. So I'm doing pretty well with my indicative content. If you were doing this in an exam, it probably would be worth just writing a little bit more to explain what you're doing. But we've picked up all the indicative marks there, and so that's a 6-mark answer. Okay, so we've got phenol here, and the first thing that you should be thinking about is the reactivity of phenol. So it's more reactive than just a benzene ring by itself, because this lone pair on the oxygen is able to interact with the delocalized system. It joins into the delocalized system, and this means that there's greater electron density and it's more susceptible to electrophilic attack. So if we take phenol reacting, you don't need such severe conditions as you would need with benzene. So we've got the reaction with bromine water in part A1, and hopefully you know that you get tri-substitution rather than mono-substitution. So let's draw our organic product. We've got our ring system. That's not going to change. We're not going to lose the delocalization, because that would, if we did, we'd be losing stability. So it's not energetically favourable for that to happen. And we would get bromine atoms joining on. So they've substituted for the hydrogens that were on those corners, which means that we've lost 3 lots of hydrogen, and they form HBr. So we've got over here 1 mark for our structure of 2,4,6 tribromophenol, and then 1 mark for the balanced chemical equation. Okay, so compare and contrast the bromination of phenol with the bromination of benzene. It's not asking us for the mechanism here, but I'm going to draw it anyway, just for background, and it wouldn't do you any harm to have written it in your answer. So we've got a benzene ring here, which we've already said is less reactive than a phenol, because we haven't got that extra lone pair from the oxygen. And so rather than it just reacting with bromine solution, as we get here, you need to have a halogen carrier, which is effectively a catalyst. So we'd have FeBr3 as the one that we use for bromine, for bromination. And what happens is that the bromine, effectively, we get an association between the ion and the extra bromine atom here, so FeBr4 minus, so the halogen BR-BR bond is effectively broken to leave us with this funny species Br plus, which is an electrophile because it can accept a pair of electrons, and it's positive, so it's attracted to the electron density in the ring. And in the second stage, we get that attack and an intermediate, which would have both a hydrogen and a bromine on there, and that disrupts the delocalized system. So the delocalized system can't go beyond these 2 carbons, because this carbon's already got 4 bonds now, and that's now positive. It's picked up the Br+. And in our final stage, we can lose that hydrogen. H+ goes in there, and the way it would actually happen is you'd have your Br that's on your Fe Br3, and that bond is broken to join to the hydrogen, but you wouldn't need that much detail. So here's our final product. Okay, and we've reformed our catalyst. Our FeBr3 is back, and we've got HBr as well. Okay, so let's do our compare and contrast. First of all, they're both electrophilic substitution reactions. That's worth saying. But big difference, we get mono substitution here with benzene. So only one hydrogen is substituted for bromine. Whereas with phenol, we've just drawn it. We've got tri-substitution. 3 hydrogens are replaced by bromines. So that's worth putting in. And also the conditions we've already said are very different. So with phenol. So we've said that we can just use aqueous bromine for phenol, whereas here we need to have bromine liquid alongside this halogen carrier or catalyst. So and you'd also heat it or under reflux really. So there's a number of things that you could say. Let's say halogen carrier needed, which is the FeBr3 for reaction with benzene, but only aqueous solution needed for reaction with phenol, and that would do. Right, part B. So phenol can be nitrated to produce 4-nitrophenol. Mechanisms of nitration of phenol and of benzene are similar. Complete the diagram using curly arrows to show a possible mechanism for the reaction and phenol to produce 4-nitrophenol. Okay, so yeah, so this NO2 plus ion is actually usually formed by reacting concentrated nitric acid and concentrated sulfuric acid. You could be asked that, although they're not in this question, so we're not going to worry too much. The electrons go from the ring, the region of electron density, and attack the nitrogen. Okay, so the positive charge is actually on the nitrogen, and it's the nitrogen that ends up attached to the ring. So we have to make sure our arrow is joined to there. And that means that we have to disrupt the delocalized system. It can only go round to these 2 carbons because, like in the previous one, we've now got a carbon with 4 bonds. So we've got NO2, and that's positively charged. And we want to restore the delocalized system because that provides it with extra stability. So in the final stage, we have those electrons from the hydrogen, the carbon-hydrogen bond, going back into the ring to give us our product. Okay, so 3 marks. We get 1 mark for the electron pair movement from the ring to the electrophile, 1 for the formula of the intermediate ion, so make sure you get the position of the delocalized system right, and then final 1, losing the H plus, that arrow, and forming a product. And don't forget the H plus has come off, so I ought to really write it down there. Okay, what is the mass in grams of 4-nitrophenol produced from 0.94 grams of phenol if the yield of this isomer is 15%? Okay, so we have got 0.94 grams of phenol. Let's work out moles of phenol. Equals mass over MR. So the MR of phenol, we've got 6 carbons plus 1, 2, 3, 4, 5 plus 1 there, so 6 hydrogens plus an oxygen. 0.94 divided by 6 times 12 is 72, plus 6 is 78, 88, 94. Oh, okay. Easy numbers. So we get 0.01 moles of phenol. Now it's going to be a 1-to-1 ratio, so if it's at a 100% yield, then we're expecting 0.01 moles. It's 15%, so let's put the percentage in now. So we're expecting 0.15 times 0.01 moles. Which gives me 1.5 times 10 to the minus 3 moles. Okay, so mass that we're going to make equals moles times MR. 1.5 times 10 to the minus 3 times the MR of the nitrophenol, which is 6 carbons. So 6 times 12 plus 1, 2, 3, 4, 5 hydrogens plus 1, 2, 3 oxygens plus 1 nitrogen, and we put that through our calculator. So 6 times 12, 72 plus 5 plus 3 times 16 is 48 plus 14 times 1.5 times 10 to the minus 3 gives us 0.2085. So have a look at our values over here. Well, rounded to 2 decimal places, that's B. Okay, 2 structural isomers of 4-nitrophenol which have a benzene ring. Okay, so we've got the one where the nitro group is on carbon number 4. So we could also have it on carbon number 2 or carbon number 3. So I'd always number with the phenol on number 1. So let's draw our 2 possibilities. There's our OH. Oh. NO2 on there. That would be identical to having it on there instead. It's just flipped over. Or it can be on carbon number 3 like that. Okay, which again would be identical to having it on that one. So 1 mark for both. Okay, so we've got an analysis question of a carboxylic acid and then 3 suggestions of what it could be. So worth just having a look at those structures and thinking about it before you even start. This one, characteristic features, there's 2 COOH groups and 1 carbon-carbon double bond. This one has got the 1 carbon-carbon double bond, only 1 COOH group. And 1 carbon-carbon double bond again. And then on this side we've got an OH group. And over here we've just got a straight chain and 1 COOH group. Okay, and we're asked to look at the IR spectra. Oh, sorry, we're given an IR spectrum and we're asked to predict which wave number ranges it would contain. So any carboxylic acid group is going to contain that C double bond O and the OH. So let's write them down before we even start and then find them in the data book. So here's the data book. We are looking for, here we go. Okay, so the carboxylic acid OH stretch is 3,300 to 2,500. So we'll write that in straight away, 3,300 to 2,500. And then C double bond O, let's find it, is, here we go. So we're looking for carboxylic acids. Aryl means it contains a ring. Anhydride, that's not what we're looking at, that's a different functional group. So it's an alkyl carboxylic acid, 1725 to 1700. So 1725. To 1700, and then we ought to put the units in really. Okay, so that's that bit done, fairly straightforward. One of the students suggests that this infrared spectrum in the data booklet alone could be used to identify which of the 3 proposed structures is X. Show that the student's suggestion is correct by including relevant IR data in your answer. Looking at this as I marked your answers, lots of you quoted correct values from the data book but didn't really explain what you were doing. So we've already done the working out here, haven't we? We've said what groups we've got. So structures 1 and 2 will both contain that alkene group, whereas structure 3 won't. So I'm going to start there. So structures 1 and 2 both contain CC. Okay, so let's go to the data book and find out what that absorption would be. So here we go, triple bond, double bond, here we go. So isolated alkene 1669 to 1645. Okay, so structure 1 both contain CC, so we will see this. And it's not seen for structure 3. Okay, let's look at what else we've set up here. So we really need to distinguish structures between structures 1 and 2 now. So 1 and 2, what is the difference? Well, structure 2 has got the alcohol OH, whereas structure 1 will just have the carboxylic acid OH. So structure 2 contains alcohol OH group. And looking at our data booklet, that gives us 3750 to 3200. Okay, whereas we've already said that it doesn't contain the carboxylic acid OH, and if we look in the data book, the carboxylic acid OH stretch is different, so 3,300 to 2,500, so we wouldn't be confusing the two. So structure 2 contains our alcohol OH bond, and whereas structure 3, worth just saying at the end, won't contain either of those two, the C11C or the OH. And we're done. So 1 mark for each sentence there. Okay, so this leads us on to a calculation, and we've got an acid-base titration to find further information about X. We've got solid sodium hydroxide used to make up our solution. Calculate mass in grams of sodium hydroxide each student should weigh out to prepare 250 centimeters cubed of 0.140. So we've got the concentration and the volume. We need to find the number of moles, then we can use moles equals mass over MR. So moles in solution equals concentration 0.140 times the volume we're trying to make, and we're working in centimeters cubed here, so I need to divide by 1,000. So we'll put that through our calculator to get the number of moles. 0.14 times 250, 0.035 moles. Okay, and I use moles equals mass over MR, mass equals moles times MR, 0.035, and we're looking at sodium hydroxide, which is sodium 23.0 plus 16.0 plus 1.0, and so times gives us 1.4 grams. So straightforward answer there. Part C. Loads of information again, so probably worth going through and just highlighting important things as we go. Each of the students makes up their solution. Okay, that's the same values as before. So in their volumetric flask, titrates the solution with the same solution of X of known concentration. Okay, so student A has got sodium hydroxide 10 centimeters cubed in the conical flask, and the burette contains X, and the mean titer is 10.20 centimeters cubed. B, we've got, oh, interesting. So they've added a bit more distilled water to the volumetric flask, and notices that they filled it several centimeters cubed beyond the graduation mark. So they're basically incompetent. And so then they remove the extra solution and discard it. That's always a bad idea, because when you remove the solution, you're not just removing water, you're also removing some of the sodium hydroxide. So I'm going to just make a note of that now. So their concentration is going to be lower than they think. So lower than 0.140 molar. Okay, and they're doing something similar, 10 centimeters cubed in the conical flask, X in the burette. Student C correctly prepares the solution, washes the conical flask, pipettes 10 centimeters cubed of sodium hydroxide into the wet conical flask. Okay, that doesn't really matter. Titrates the contents of the conical flask with the solution of X. So how does student B's mistake affect the value of the titer? Well, by removing that extra water, they've actually removed some sodium hydroxide with it. We've already said the concentration therefore is lower. If the concentration of the sodium hydroxide in the conical flask is lower, there are fewer moles of sodium hydroxide in the conical flask. So let's put that. So fewer moles of NaOH in the conical flask, which means that they're going to need less of the acid to neutralize it. So fewer moles of X needed, i.e. the titer will be lower. Titer smaller. Okay, and looking at the mark scheme, it says, hang on. Yep, so we get 1 mark for fewer moles of NaOH in the conical flask, or we could say sodium hydroxide is more dilute, that would be fine. Therefore, the titer is smaller, so we've got 2 marks there. Explain how, if at all, student C's use of a wet conical flask affects the value of the titer. Well, it doesn't affect it because having water in the conical flask doesn't change the number of moles of sodium hydroxide. So I'm going to say moles of sodium hydroxide in the flask is the same. So therefore titer is the same. And we get 1 mark for each. Okay, so we're looking at student A, so it's worth having that information about student A ready to look at. And we're told some uncertainties. The burette has an uncertainty of plus or minus 0.05 centimeters cubed for each volume reading. That's important because there were 2 readings, the starting volume and the final volume. Volumetric flask, plus or minus 0.30, that's for the whole volume, so we don't need to worry too much, that's only going to be once, and 0.04 for the volume for the pipette. Okay, so percentage uncertainty is going to be the uncertainty divided by the reading times 100. Okay, each time. Now let's start with the burette. There's 2 readings, so I need to multiply it by 2. So burette percentage uncertainty equals 2 times plus or minus 0.05 divided by what the reading was. So I go and have a look. It was 10.20 centimeters cubed times 100, and I put it through my calculator. So 2 times 0.05 divided by 10.2 times 100, and that gives me 0.98%. Okay, let's then look at the volumetric flask, since that's next. So volumetric flask, percentage uncertainty is going to be, there's only 1 reading, so 0.30 divided by the volume that goes in the volumetric flask. So if I go back to my information again, it's 250 centimeters cubed are made up. So we divide by 250 and put that through the calculator. .12%. And then final one is our pipette. Again, only one reading, so we do plus or minus 0.04, and we need to look up what the volume was in the pipette. So back to student A, and they take 10.0 centimeters cubed with the pipette. So we're dividing by 10, and in our calculator that is 0.04 divided by 10 times 100. Oh. And that's 0.4%. Okay, so looking at that, we're asked which has the lowest percentage uncertainty. It is this one. So the volumetric flask. And we get 1 mark for that, so identifying that bit. And we get 1 mark for having these 2 percentage uncertainties correct, because that's easy because there's only one reading. 1 mark here, basically really for identifying that you multiply by 2, and there are 3 marks. Okay, so moving over the page. Student A calculates the correct value using the mean titer. The results indicate that X has structure 1. Write the equation for the reaction between structure 1 and sodium hydroxide. Okay, so we've got a carboxylic acid. I think it's sometimes worthwhile just drawing it out in a bit more detail so you know what it looks like and you don't make any silly mistakes. So we've got CH, CH, and then COOH. You're not going to lose any marks for writing it out in full like this. And so there are 2 carboxylic acid groups. Acid plus alkali goes to salt plus water. So these are the acidic protons, the ones that are lost. So we're going to react it with 2 OH minus ions. It asks us for sodium hydroxide, so I'm going to write sodium hydroxide. I'm going to need 2 lots of them. And so we're going to form, there's the O minus Na plus C dot bond O, C, put everything on. There we go, O minus Na plus water. Okay, and we're going to need 2 lots of water because we've got 1, 2, 3, 4 hydrogens over there, 4 over here. Okay, you could rewrite that again if you want, just to make it look a bit neater, but it's fine to have it like that. But if you're writing it out more neatly, you'd just go for this. NaOH goes to, now we've got the Na on the front, OOCCH. There we go. And 1 mark is for the left-hand side, 1 for the right-hand side. Deduce the value that would have been obtained for the mean titer if the structural formula of X had been structure 2. So let's go back to structure 2 and have a look. Right, structure 2 has only got 1 carboxylic acid group versus 2 on the first one, which means that structure 2 is going to react with half as much sodium hydroxide. Okay, so this was a 2-to-1 ratio, this will be a 1-to-1 ratio. So we need to go back to our method and just remember what was in the flask, what was in the burette. So the burette contained the acid X. Okay, so if the burette contains structure 2, you're going to need twice as much of structure 2 to react with the same quantity of alkali. Okay, so the titer would be doubled, i.e. 20.40 centimeters cubed, because structure 2 has only one carboxylic acid group. Therefore, the ratio in the equation is 1:1 of acid to NaOH is 1:1 rather than 1:2. Okay. Okay, then a more straightforward question. Chemical tests complete the table to show whether the structures react with bromine water and when heated with acidified potassium dichromate. So think carefully about what these are testing for. Bromine water is a test for unsaturation, isn't it? A test for C double bonds. And acidified potassium dichromate is an oxidizing agent. It oxidizes primary and secondary alcohols and aldehydes. I'm not sure aldehydes are going to be necessarily relevant here. We've already said that this contains carboxylic acid groups. Well, that's not going to have any effect with the bromine water or the potassium dichromate, but the double bond is going to react with the bromine water. So yes, we get a reaction. No, we don't. Here, yes, we've got a double bond. We have got an alcohol group, and it's a primary alcohol. It's going to react. Here, we haven't got a double bond, and we haven't got an alcohol group. We get 1 mark for this column, 1 mark for this column. Okay, so on to part F. Stereoisomers, EZ. Okay, so we need to look at the double bond. E stands for entgegen in German, which means opposite, whereas Z stands for zusammen, together. You can remember it as Same-Side, so with Z, they're on the same side of the double bond. Okay, so here's our double bond, put the double bond in the middle. So the E isomer is going to be like that, whereas, there we go, COOH. Whereas the Z isomer, carboxylic acid groups on the same side. State why there are EZ isomers. Okay, well, because there are 2 different groups on each carbon, and because there's restricted rotation about the double bond. So 2 different groups, because of course you don't get EZ isomers if the groups are the same on either of the carbons. Oh, so 2 different groups on each of the C atoms in the double bond. And that's going to be your first mark, and second mark, restricted or limited rotation about the C double bond C. Okay. The reason for that is the second part of the bond. The first part of the bond is a sigma bond. The second is a pi bond, which requires overlap of 2 of the lobes like that. As soon as you rotate, the lobes won't be overlapping, so the double bond breaks. So if you've got a double bond in place, the angle needs to be right and it can't rotate from that angle. So moving over the page, student A calculates the correct value using the mean titer. The results indicate that X has structure 1. Write the equation for the reaction between structure 1 and sodium hydroxide. Okay, so we've got a carboxylic acid. I think it's sometimes worthwhile just drawing it out in a bit more detail so you know what it looks like and you don't make any silly mistakes. So we've got CH, CH, and then COOH. You're not going to lose any marks for writing it out in full like this. And so there are 2 carboxylic acid groups. Acid plus alkali goes to salt plus water. So these are the acidic protons, the ones that are lost. So we're going to react it with 2 OH minus ions. It asks us for sodium hydroxide, so I'm going to write sodium hydroxide. I'm going to need 2 lots of them. And so we're going to form, there's the O minus Na plus, C double bond O, C, put everything on. There we go, O minus Na plus water. Okay, and we're going to need 2 lots of water because you've got 1, 2, 3, 4 hydrogens over there, 4 over here. Okay, you could rewrite that again if you want, just to make it look a bit neater, but it's fine to have it like that. But if you're writing it out more neatly, you'd just go for this. To NaOH goes to, and now we've got the Na on the front, OOCCH. There we go. And 1 mark is for the left-hand side, 1 for the right-hand side. Deduce the value that would have been obtained for the mean titer if the structural formula of X had been structure 2. So let's go back to structure 2 and have a look. Right, structure 2 has only got 1 carboxylic acid group versus 2 on the first one, which means that structure 2 is going to react with half as much sodium hydroxide. Okay, so this was a 2-to-1 ratio, this will be a 1-to-1 ratio. So we need to go back to our method and just remember what was in the flask, what was in the burette. So the burette contained the acid X. Okay, so if the burette contains structure 2, you're going to need twice as much of structure 2 to react with the same quantity of alkali. Okay, so the titer would be doubled, i.e. 20.40 centimeters cubed, because structure 2 has only 1 carboxylic acid group. Therefore, the ratio in the equation is 1-to-1 of acid to NaOH is 1-to-1 rather than 1-to-2. Okay. Okay, then a more straightforward question. Chemical tests. Complete the table to show whether the structures react with bromine water and when heated with acidified potassium dichromate. So think carefully about what these are testing for. Bromine water is a test for unsaturation, isn't it? A test for C double bonds. And acidified potassium dichromate is an oxidizing agent. It oxidizes primary and secondary alcohols and aldehydes. I'm not sure aldehydes are going to be necessarily relevant here. We've already said that this contains carboxylic acid groups. Well, that's not going to have any effect with the bromine water or the potassium dichromate, but the double bond is going to react with the bromine water. So yes, we get a reaction. No, we don't. Here, yes, we've got a double bond. We have got an alcohol group, and it's a primary alcohol. It's going to react. Here, we haven't got a double bond, and we haven't got an alcohol group. We get 1 mark for this column, 1 mark for this column. Okay, so on to part F. Stereoisomers, EZ. Okay, so we need to look at the double bond. E stands for entgegen in German, which means opposite, whereas Z stands for zusammen, together. You can remember it as same side, so with Z, they're on the same side of the double bond. Okay, so here's our double bond, put the double bond in the middle. So the E isomer is going to be like that, whereas, there we go, COOH. Whereas the Z isomer, carboxylic acid groups on the same side. State why there are EZ isomers. Okay, well, because there are two different groups on each carbon, and because there's restricted rotation about the double bond. So two different groups. So of course you don't get EZ isomers if the groups are the same on either of the carbons. Oh, so two different groups on each of the C atoms in the double bond. And that's going to be your first mark, and second mark, restricted or limited rotation about the C double bond C. Okay. The reason for that is the second part of the bond. The first part of the bond is a sigma bond. The second is a pi bond, which requires overlap of two of the lobes like that. As soon as you rotate, the lobes won't be overlapping, so the double bond breaks. So if you've got a double bond in place, the angle needs to be right and it can't rotate from that angle. Okay, question 7. We've got a nice weak acid-base equilibria question by the looks of it. So we've got a weak acid, given its Ka value. I'm just going to highlight these because I know that I'm going to need to use them in my answer. We've got a solution mixing particular volume and concentration of sodium hydroxide, so a strong alkali with a particular volume and concentration of HX, and we need to calculate the pH. Okay, so this is a nice acid-base equilibria question. So I'm reacting HX with NaOH to start with. That's the first reaction that's happening. So I'm going to form NaX plus H2O. The products don't matter too much, although I'm going to keep in the back of my head that Ka equals, for a weak acid, concentration of H plus multiplied by concentration of the counter ion X minus divided by the concentration of the undissociated, X, the undissociated acid. Okay, now that means that when I make this salt, it's an ionic salt, so it's going to split up into Na plus and X minus. That value is going to be important because it comes in here. The concentration of H plus and the concentration of X minus is not going to be equal because we're making some X minus in this reaction. Concentration of HX is going to be dependent on however much of this is left over at the end. Concentration of H plus is going to be what I'm going to want to get in order to get the pH, because I'm given the Ka, so the concentration of H plus is the only thing that's left over at the end. So I'll find that and then use pH equals minus log to the base 10 multiplied by concentration of H plus. So I would set this up with initial moles and think about what's going on. So HX, we have got 25 centimeters cubed times 0.92, and I'll use my conversion factor to get the moles. Yep. 25 times 0.92 divided by 1,000 gives me 0.023 moles. Let's get our moles of sodium hydroxide. So I've got 10.5 times 0.8 over 1,000. May even be a good idea to tick off what you're using as you go, because you should be using all the information in most questions. So I've ticked off that so far. 10.5 times 0.8 divided by 1,000. 8.4 times 10 to the minus 3. So that's obviously the smaller of the two values, which is probably what I would expect in a question like this, for the alkali to be all used up and the HX to be the one in excess. So let's think about what's happened. If this is the limiting factor here, and it's a 1-to-1 ratio, and it's a 1-to-1 ratio of this and this, 8.4 times 10 to the minus 3 moles of this have been used up. Okay, so I could put the change is going to be minus 8.4 times 10 to the minus 3 moles. Same with the acid. So we're going to have minus 8.4 times 10 to the minus 3 moles used up. On this side, I've made 8.4 times 10 to the minus 3 moles of the salt. Sorry about this in the way. And the water, I'm going to ignore the water. The water is not going to be important. So at the end, so equilibrium moles is better than final moles. Equilibrium moles or final moles, doesn't really matter, is 0.023 minus 8.4 times 10 to the minus 3, 0.0146. Sodium hydroxide, 0, it's all gone. And this one is going to be 8.4 times 10 to the minus 3 moles. Okay, now the next stage, now I've got the moles, is to put it into this equation. And you can calculate, you need concentrations here. And we know that concentration is moles over volume. So I could calculate it. I have got the total volume of solution, 25 plus 10.5. But actually looking at this, I can see that the volumes are going to cancel. So let me show you. Ka equals concentration of X minus. So concentration being moles, 8.4 times 10 to the minus 3, divided by the total volume. I'll just put it as V for the moment. Multiplied by the concentration of H plus, divided by concentration of HX, so moles divided by volume. And those two V's now in my equation cancel. Okay, so it'd be okay if you worked out all of the volumes and worked out the concentrations, that would be fine. But it is actually just a quicker route to do it this way. And now I'm going to rearrange. I've got the value for Ka, 5.25 times 10 to the minus 5. Okay, so I can tick off another piece of information that I've used in my information there. And I'm going to rearrange to get concentration of H plus. So concentration of H plus equals 5.25 times 10 to the minus 5 multiplied by 0.0146 divided by this value, 8.4 times 10 to the minus 3. Put it through your calculator. So 5.25 times 10 to the minus 5 times 0.0146 divided by 8.4 times 10 to the minus 3. And I get 9.125 times 10 to the minus 5 moles per dm cubed, because it's concentration. Okay, and I'm well on my way. So final stage now, pH equals minus log to the base 10 concentration of H plus. So minus log 9.125 times 10 to the minus 5. And so into my calculator gives me 4.04 as my pH. And remember that pHs should always be equated to 2 dP. Okay, so let's go to the mark scheme and just identify where we get marks. So mark 1 is for calculating the moles of X minus present in the mixture. So that's this. So that's, oh sorry, not this, that's this. So that's one mark there. Calculating moles of HX unreacted, that's there. Okay, so laying it out like this, you can see what everything is. It's fine to do this and you will be given the marks. Calculating ratio of concentration of HX to X minus, or ratio of moles, and cancelling V. So that's down here. Rearranging the Ka expression correctly and substituting appropriate values. So here we go, there's our values down here. And then 1, 2, 3, 4, final pH to 2 significant, to 2 or 3 SF it says, so they're being a bit lenient here, but you should go for 2 dP always with 0 pH value. Okay, so it's not as hard as it looks, but it does take a while. Take your time doing those. Okay, so we've got a titration curve here, and they're a bit trickier than they look. Sometimes you just think you can just sketch out the vague shape, but you actually need to do a bit of thinking about this. So here's the thinking. We have got a strong alkali, that's worth noting immediately. So we're expecting to get quite a high pH when we add the alkali. We've got a weak acid, Okay, and first thing to think, what's being added to what? We've got the alkali added to the acid. So we're going to start with a lowish pH, but not all that low, because it's a weak acid. So starting marker, I'd guess around pH 3 for a weak acid. Sometimes you can calculate it because you could be given a Ka value and they need to have enough information to work out the initial pH there, but we're not given a Ka, so we're expected to guess it. We also, the second marker is thinking about the equivalence point. So immediately I notice we've got the same concentration of the two solutions, but we've got twice as much alkali as acid. So as soon as 25 centimeters cubed of the alkali have been added, we're going to have neutralized our acid. So our equivalence point is at 25 centimeters cubed, and that's our second marker. Okay, and then our third marker is going to be the pH of the final solution. You could do a big calculation here, or you could take a guess. If you're going to take a guess because you're a bit short of time, then I would be thinking that 1 molar strong acid, 1 molar sodium hydroxide has a pH of 14. And it's slightly less concentrated than that, so it's not going to be quite as high as 14, so I'd guess around 13. Alternatively, you can do a calculation, so I'll show you on a separate piece of paper a quick calculation for this. Or maybe not quite so quick, but let's do it anyway. So we have got, at the end, we're going to have moles of sodium hydroxide. The equivalent volume of sodium hydroxide left over is going to be that 25 centimeters cubed. So it's going to be 25 times 0.1 over 1,000 to get the number of moles of sodium hydroxide left over. So I put that through my calculator. I probably don't really need to put it through my calculator. 2.5 times 10 to the minus 3. Now that's the number of moles, and it's now dissolved in a total volume, so 75 centimeters cubed of solution in total. It's water now and salt solution. So in 75 centimeters cubed of solution. So the concentration is going to be the number of moles times 1,000 divided by the total volume. So 2.5 times 10 to the minus 3 times 1,000 divided by 75, 0.03 dot dot dot. Okay, and that's going to be the same as the concentration of OH minus ions, because NaOH is a strong alkali, and so it splits up completely into Na plus and OH minus. So I can put this in here. And then the next thing to remember is that to get the pH, which is what we want on our curve, we're going to use minus log concentration of H plus. We haven't got concentration of H plus, but we can get it from the ionic product of water. So ionic product of water, H plus concentration times OH minus concentration, which equals 1 times 10 to the minus 14. So concentration of H plus equals 1 times 10 to the minus 14 divided by 0.03 dot dot dot. And let's calculate. So 1 times 10 to the minus 14 divided by what we had in our calculator gives me 3 times 10 to the minus 13. And now I just substitute that into my pH expression. So pH equals minus log to the base 10 concentration of H plus. So substitute it in, gives me minus 12.5, sorry, 12.5. So that's my final marker on my graph. So 12.5, 13 is midway between, so 12.5 is about here. This is just a sketch, so it doesn't need to be perfect. Okay, now we know at the equivalence point, that's when you get your vertical section. So weak acid to start with, it's gonna, pH is going to rise. Let's get to the equivalence point, then it's going to rise really sharply, and then again at the end it remains reasonably constant. It increases only slowly like that. So something like that, you get the marks for pH starting between 2 and 4, a general shape that ends at pH 12 to 13, so we've got the right kind of shape and we're ending between 12 and 13. So again, you can guess, you don't have to calculate. Any vertical at 25 centimeters cubed, so we've got our equivalence point 25 and there's our vertical, and then vertical that runs through no more than 5 pH units, 1, 2, 3, 4, we're fine, and runs through 6 to 7, there we go, and our 10 up here. So we're okay with our fourth point. Okay, so then we're asked to explain how we would use the graph to obtain the value of the acid dissociation constant for propanoic acid. We're not expected to calculate the value. This is a classic question because when you have a titration curve, you would have used this. You can use the half neutralization point to work out the Ka value. Okay, so worth learning. I'll prove it to you again on a separate piece of paper in a minute. Here's our equivalence point. Our half neutralization point is therefore at 12.5. So 12.5 is here. And we could read off our pH at the half neutralization point. So how are we going to use the graph? Read off the pH at the half neutralization point. i.e. when 12.5 centimeters cubed of NaOH is added. Okay, and then we need to say pH equals pKa. Okay, that's the case at the half neutralization point. And now we need to do a bit of rearrangement of our equation. So pH is what I've got on the graph, so I don't need to do any rearrangement there, but I want to get Ka, so I want to get rid of the Ka. And the P just means minus log to the base 10 of Ka equals pH. So therefore Ka equals 10 to the minus pH, and that's what they're looking for in the answer. So 1 mark for having that kind of expression, or to be honest, you could actually have got it from that top bit, and 1 for mentioning the half neutralization point or the half equivalence point, or 12.5 centimeters cubed. So we've actually been more thorough than we need to be. Okay, so I said that I proved that pH equals pKa at the half neutralization point. So to do that, let's consider a weak acid. So we've got a weak acid, HX, and we're reacting it with, we'll say NaOH, that makes it nice and straightforward. And we have to have twice as many moles of the HX as we've got of the NaOH. Okay, so this is initial moles. Okay, because the whole point is that I'm only neutralizing half of the HX. So in our reaction, we know that we would produce our salt, NaX, plus water. Okay, and initially, at the beginning of the neutralization, we wouldn't have any moles of salt or water. Okay, so the change, because this is the limiting factor, it will be all used up. So we're going to have minus x over 2 moles of NaOH used up. That means that the same quantity of HX is going to be used up. It's going to mean that we make x over 2 moles of sodium hydroxide, sodium X, and we are going to make x over 2 moles of H2O. So our final moles, so this is just the same method that you do if you were doing a normal calculation with numbers rather than algebra. X minus x over 2 leaves us with x over 2 left over. No sodium hydroxide, x over 2 moles of NaX, and x over 2 moles of water. Now this bit is not really relevant because water isn't involved in the Ka expression, but this is relevant because this is an ionic compound. So when it dissolves, it's Na plus ions and X minus ions, and of course the X minus does appear in your Ka expression. So next job, I'm going to write out my Ka expression. So Ka equals concentration of H plus multiplied by concentration of X minus divided by the concentration of the undissociated acid. And I'm going to substitute in some values here, well, algebraic values. So we need concentrations. I've only got moles, so I'm going to say my total volume afterwards is V. Okay, so I'm going to say V decimeters cubed because that just makes life a bit easier. And concentration is just the number of moles per decimeter cubed, so I can calculate it using number of moles divided by V. So let's put in our values. Concentration of H plus, I don't know. Okay, and think about it, I'm going to want to get that in the end, to get pH. Concentration of X minus is X over 2, so multiplied by X over 2V, I'm going to put, so 2, the V is on the bottom, so I've effectively divided the moles by the volume to get the concentration there. And then divided by concentration of HX, which is X over 2V again, okay, because moles divided by concentration. And you'll see, looking at this, that these two cancel. They're exactly the same value. So at the half neutralization point, Ka equals concentration of H plus. Okay, and so on a pH curve, let's change, because I know concentration, we know concentration of H plus is related to pH using the expression minus log to the base 10, concentration of H plus. So if I do that to both sides of my equation, I can say minus log Ka equals minus log to the base 10 concentration of H plus. And we give that the name pKa, don't we? And we call this pH. So we've made our expression here, pKa equals pH at the half neutralization point, and we've already talked about how we would rearrange that. Okay, so question 8 about the iodine clock reaction. Again, this is a core practical, so it should be really, really familiar. Make sure you really go over your core practicals using that paper 3 revision pack. State why the order of reaction with respect to iodide ions cannot be 5, even though 5 moles of iodide ions are shown in the equation. Well, straight away you should know that the mole ratios in the chemical equation are not related in any way to the orders of reaction. Don't make that mistake. And you should also know that the order with respect to a particular species tells you how many molecules of that species, or how many ions of that species, if it's an ion, are involved in the rate determining step. And think about it, if the order with respect to iodide ions are 5, that would mean that 5 iodide ions come together at the same time in the rate determining step, and the chances of that happening are ridiculously low. So you need to show an understanding of what the order of reaction or order with respect to a particular species means by saying that order 5 means 5 I minus ions involved in the rate determining step, but the probability or the chance of this many ions colliding is negligible, i.e. 0. Okay, so there's our answer. Okay, so part B, we've got some data here, and we're told some important things. Always worth, again, highlighting things that you're told. So we're trying to find the order of reaction with respect to the iodate 5 ions. We're told the concentration of iodide ions and acid were in large excess. That's important because it means effectively their concentration isn't changing. So the order with respect to iodide and the acid isn't going to affect the rate in this particular instance because the concentration is going to be the same in each case. So that means that we can focus in just on the iodate 5 ions and work out how the concentration of iodate 5 affects the rate. So we're varying the concentration of iodate 5 by changing the volume of the iodate 5 solution. And as long as we keep the total volume of solution constant, the volume of iodate 5 solution is going to be proportional to the concentration of iodate 5. Obviously, if you start changing around the total volume of solution, the concentrations, you're going to have to do a more complicated calculation to get them. So this means that it's really straightforward, and this is what the first question is getting at. So in experiment 6, the student forgot to add deionized water to keep the total volume the same for each experiment. State why the total volume should be kept the same. Well, so that the concentration of iodate 5, so iO3 minus, is proportional to the volume of iodate 5. So it's useful for plotting the graph, isn't it? Because you then don't need to do a calculation and plot concentration of iodate 5, you just plot the volume of iodate 5. So it's proportional to volume of iodate 5, and that would get you the mark. Okay, complete the table, use the results to plot a graph of 1000 over T, so that's proportional to the rate, against volume of iodate 5 ions. I don't think anyone had any problem really doing the calculation here. You just have to do 1000 divided by that value on your calculator. So I'm not going to bother to go through that. I'm just going to look up the values in the mark scheme. Yeah, so you should have 3.85 here, and look at it, the others are quoted to 2dp, so quote these to 2 decimal places. It's silly to be inconsistent. Okay, so you may have to do a bit of rounding. Okay, and then we're going to plot our graph over the page. Now again, plotting a graph should be really, really easy marks, but just read it carefully. So plot a graph of 1000 over T against volume of iodate 5 ions. When it's written this way around, you always write the Y first, so it's the Y against X. So that means we have got on the Y-axis the 1000 over T, which is proportional to the rate. So let's label our axis already. So we've got 1000 over T, and then we should have the units as well, because you always include units, so that's in seconds to -1. And then on our x-axis down here, we're going to have the volume, we're told this, of iodate 5, and of course that's in centimetres cubed. And then you just need to plot a suitable scale. So looking at my number of squares that I've got and the range of values, on my x-axis, I want my values to go between 1 and 10. Oh, in fact, we're ignoring 5, 6, so I don't need to worry too much about that. So 2 and 10, not that makes any difference. 1, 2, 3, 4, 5, 6. I would say probably you're going to want a scale that is something like 0. I'm going to go back and look at the, so it's all to 1 decimal place. So I'm going to put 0, 2.0, 4.0, 6.0, 8.0, 10.0, etc. I'll fill it in even though I know it doesn't go this high. Okay, and on my y-axis I need to go up to 5.56, so about 6, and down to about 1. So 1, 2, 3, 4, 5, 6. That's easy to do. I'll just make every large square 1 unit. So they tend to make these fairly straightforward to draw your graphs with. So don't make it difficult for yourself by doing some kind of strange scale. So let's have 1.00. Really, I ought to quote it to 2 decimal places since that's what I've got in the table. 3.00, 2.0, 5.00, and 6.00. And then I'm just going to plot my points. So let's go back to the page and get our values. Okay, so we should have, first point is 10 centimetres cubed of iodate solution and 5.56. So 5.56, really should be plotting with a pencil rather than a pen, but never mind. 7 centimetres cubed, and that's the one that's 3.85. So I'm down in the middle here, 3.85. 5 centimetres cubed, so we're down here, and 2.80. So that's exactly on the point there. And 3 centimeters cubed and 1.65, so 165, and 2 centimeters cubed, 1.11, so 1.11 out there. And I can see I've got a really nice straight line. So I'm just going to join it all up, and it clearly goes through the origin. So this is a very easy graph to do. Again, use a ruler. Having a clear ruler is really helpful, so you can see if the lines are not quite so straightforward as that. Marks are for firstly having the values in the table, secondly having the axes the right way around and labelled, so we've got that here. Thirdly, having a suitable scale, so that's the kind of scale that covers at least half of the graph paper, half the axes, so that's fine. And then all points plotted correctly to within plus or minus half a square with a best fit straight line through the origin. So we've got full marks for that. Okay, deduce the order of reaction with respect to the iodate 5 ions and justify your answer. So looking at this, 1000 over T is proportional to rate, and my volume of iodate 5 is proportional to concentration of iodate 5. So I can see straight away that concentration of iodate 5 is directly proportional to the rate, which means that as the concentration of iodate 5 doubles, then the rate doubles, and we know that that's characteristic of order 1. Okay, you could fit it into the rate equation to have a look at it. So therefore, order 1 with respect to iodate 5. Okay. Okay, so we keep going. So now we've got a different version of the iodine clock where we're mixing different reagents. Reaction is first order with respect to hydrogen peroxide and iodide ions, but 0 order with respect to H+ ions. Write the rate equation, deduce the value of the rate constant. Okay, so you know that the rate equation is of the form rate equals the rate constant multiplied by each of the concentrations of the reagents to the power of whatever order they are. So hydrogen peroxide, we're told, is order 1, so I don't need to write the value. Iodide, I ignore the 2. The 2 is not important, it's just the species itself. Again, order 1. And then I don't need to include the H+, because anything to the power of 0 is just 1. So concentration of H+ to the power of 0, because it's order 0, just cancels. Hence deduce the value of the rate constant K. So let's just take some values that we've got. So we've got a value for initial rate. I want to get K, so let's rearrange straight away. So K equals rate divided by concentration of H2O2 and divided by concentration of iodide ions. The rate is 1.24 times 10 to the minus 3. Divided by concentration of H2O2 is 1.5 times 10 to the minus 3. And that's multiplied by the iodide ions, which is 2.10 times 10 to the minus 3. And I'm just going to put that through my calculator and see what I get. And then the final stage, it does ask me for units, so I just need to think a little bit at the end. So 1.24 times 10 to the minus 3 divided by 1.5 times 10 to the minus 3. Do you make sure you put in the times 10 to the minus 3? People sometimes are a bit lazy with that and lose marks. And I've got 393.65. I think 3SF makes sense. 3SF usually makes sense. I've got 3 significant figures here in my concentrations. I've got an initial rate, 3 significant figures. So I'm just going to call it 394 as my value. And then let's think about the units. So units of K, I just substitute in the units that I know. It's going to be units for rate. Well, I've got it above, but you should know the units for rate anyway. Moles per dm cubed per second, divided by 2 lots of concentration, so moles per dm cubed, times moles per dm cubed down here. Okay, and so 1 lot of moles per dm cubed is going to cancel. Anything that I bring to the top, or that's on the bottom that I bring to the top, I just reverse the sign. So I've got units of K equals moles to the -1, dm to the 3, seconds to the -1, because it's already on the top, so I'm not going to change it. Okay, and there I'm done. So 1 mark for the value, 1 mark for the units of the rate constant. So there's quite a lot of work there for just 2 marks. Okay, what's the purpose of the starch in the reaction mixture when starch is not in the rate equation nor in the reaction equation? So let's have a little look at what's going on in our equation. Having a look, the main reaction is this, and it produces iodine. Okay, so at the end of the reaction, the colour is going to go kind of a yellowy colour because of the iodine, and starch is the indicator for iodine, so you should know that starch turns blue-black in the presence of iodine. So it's a fairly straightforward answer. Starch is the indicator. But you need a little bit more than that. So it turns blue-black when iodine is produced. So it shows you when the iodine is produced. So enables measurement of time taken for the iodine to be produced. So enables measurement of time taken for I2 to be produced because it turns blue-black. Okay, and it's really important to have that second point, that idea that you are using it to measure the time taken. If you don't say that, you don't get the mark. Okay, on to looking at the Arrhenius equation. So again, a core practical of which you should know back to front, and you've seen this kind of stuff lots of times. Make sure you've gone through your core practicals. And it says, from the gradient of the graph, determine the activation energy for the reaction, include a sign in units in your answer. Okay, so my first job is going to be to measure the gradient. So I'm going to just choose some values that I think are going to make this easy to do. And I would always draw as big a triangle as possible as you calculate the gradient. I'm going to go for, well, I might as well go right to the bottom here. So there's my change in y. And here's my change in x. Okay, and I can see it's a negative gradient because of the direction of the line. So gradient is going to be equal to minus, I'll put the minus in straight away so I remember it. Change in y, I'm going from minus 0.2 to -8. So 8 minus 0.2. divided by change in x, and along here I'm going from 1.7 times 10 to the -3 across to, let's look at the axis, 1.3 times 10 to the -3. Common mistake again to leave out the times 10 to the -3. You'll end up with a much smaller value for gradient if you leave out the times 10 to the -3, so you need to be careful not to do that. Okay, so we have got 8 minus 0.2, 7.8 divided by 0.4 times 10 to the -3, negative value. Put it through your calculator, so 7.8 divided by 0.4 times 10 to the -3 equals 19500. And that's exactly actually what's on the mark scheme. They allow you a bit of leeway, which is a bit generous given that they've drawn the line, and you should be able to choose your value so you can get it exactly. They allow plus or minus 500. Okay, so now we need to get to a point where we can rearrange the equation to find EA. So if you go back to this up the top, you hopefully know that straight lines have the form y equals mx plus c. So we have a look at how this fits into that. We've got ln k on the y-axis, so there's my y, I've got 1 over t on the x-axis. That's going to be my plus c. It's irrelevant really, so that's the y-intercept. And therefore my gradient there, minus EA over R. So all we need to do now is say minus 19,500 equals minus EA over R. Okay, the minus signs cancel, and we can say EA equals R times 19,500, which is just the molar gas constant, 8.31. And so I put it through my calculator, and I get a really big number, 162,045. Really, that's a lot of significant figures to include. I'd probably just go to 3SF, so 162,000. Now that value is in joules per mole. And the reason for that is because of the units for our molar gas constant. So remember, whenever you do this kind of thing, it's worth just changing the value to kilojoules per mole, changing the units to kilojoules per mole by dividing by 1,000. So 162 kilojoules per mole. And really, really importantly, adding in the sign. The question says put a sign in and units. So it's obvious, but it's an enthalpy change. Activation energy, we always put signs for our enthalpy changes. Okay, give a reason for the point ln K equals minus 7 not being included. Well, if you go back to the table that we had, oh no, we don't even need to do that. If we just go back to our graph, there's the point at ln K equals minus 7, and it's obviously anomalous. So we ignore it. That's the case always with anomalous points, we just ignore them. Okay, so now we've got a question about finding an equilibrium constant for an esterification reaction. Again, core practical, where we've found out a Kc value, so look at your core practicals. And we're told the steps that are taken. So first job, I'm going to read through and just make sure I understand what's going on. So we've got a particular volume, and we're told the number of moles of ethanoic acid, particular volume of propan-1-ol, told the number of moles. We've got our dilute hydrochloric acid, that's got to be the catalyst in esterification, mixed together in a sealed boiling tube, so it's a closed system. And that's the pre-equilibrium mixture. It hasn't yet reached equilibrium, and we're told the number of moles of water. So there's some moles of water to start with. I guess that's probably because they were in with the dilute hydrochloric acid. The mixture's then left for a week in order to reach equilibrium. And then we do our analysis. So we transfer our mixture to a volumetric flask, and then we add some water. That's going to be important. 25 centimetre cube samples of the diluted equilibrium mixture titrated with a solution of sodium hydroxide, and we're told the concentration using phenolphthalein indicator. We're told the mean titer and the concentration of the sodium hydroxide. So first job, state the role of the hydrochloric acid in the esterification reaction. Well, we've already done that, we've already said that. It's the catalyst, so that's straightforward. And calculate the total amount in moles of acid present in the volumetric flask in the equilibrium mixture. Okay, so we need to do a bit more work now, just a titration calculation. So let's look back at what we've got. We've got our acid, I'm just going to call it HA, reacting with sodium hydroxide. It's a monoprotic acid, so it's going to be a 1-to-1 ratio. Okay. I've got my titer of sodium hydroxide is 23.60 centimetres cubed. I've got my concentration of NaOH as 0.2, and I know that I had a volume of 25 centimetres cubed of the entire equilibrium mixture. I'm not sure whether that's going to be relevant yet. So moles of sodium hydroxide is just going to be CV over 1,000. So 0.200 times 23.6. I'm going to divide by 1,000, convert that to decimeters cubed, put it through my calculator. And I get 4.72 times 10 to the minus 3 moles. Now that is in 25 centimeters cubed, okay, in the aliquot of equilibrium mixture that was used. But my question says in the volumetric flask, nicely highlighted for me, so I'm not going to forget. So that's only 1/10 of the whole volumetric flask, because I was told that the volumetric flask was 250 centimeters cubed. So I just need to multiply my answer by 10 to get the final thing. So therefore, in 250 centimeters cubed, moles of acid equals 4.72 times 10 to the minus 2. And there's my answer. And we get marks for 1 for getting this far, and then 1 just for multiplying by 10 at the end. Okay, so when we reacted with the sodium hydroxide with the acid was the ethanoic acid that was present in the equilibrium mixture and the hydrochloric acid that had been used as a catalyst, because obviously the catalyst isn't used up. So we would have expected the same quantity to be left over at equilibrium as was there to start with. And they're very generous. They give me the number of moles of HCl, which is 0.004. So therefore, I just take my answer from the previous question. So my total moles of acid was, so I'll just call it HA, because that can be HCl and ethanoic acid. 4.72 times 10 to the minus 2. Ethanoic acid was the leftover ethanoic acid, which is 4.72 times 10 to the minus 2 minus that 0.004. Okay, and we'll just put that through our calculator. 4.72 times 10 to the minus 2 minus, to be honest, you don't need a calculator for this. 4.72 times 10 to the minus 2 minus 0.004, 0.0432 moles. Okay, so part C, the initial mixture in the boiling tube contained 0.105 moles of ethanoic acid. Use your answer to calculate moles of ethanoic acid that react to form the ester in the equilibrium mixture. This is where I quite like to set it out again in the way that I would normally do an equilibrium calculation. So I'm going to write the equation at the top. I could do it with the formulae, but I'm just going to do it with the names. And I can put initial moles over here, as I always do, and I'm told that I've got 0.105 moles of ethanoic acid. I would then put the change underneath, and I'd put equilibrium moles at the bottom. And I've just calculated the equilibrium moles as 0.0432. Let's just check. Yeah. Okay, so that's what I just did in the previous question. So therefore, I just need to work out the difference there. So I do 0.105 minus 0.0432, and I get a change of 0.0618 moles, and that's been taken away. So the final answer here is 0.0618 moles. Okay, use information given in the method and your answer to calculate the amount in moles of propan-1-ol, propylethanoate and water that are present in the equilibrium mixture. So this is where I'm going to go back to the information that I started with and start to fill in my table, because I had, I've got my table in the question before. So we have got, okay, original moles of ethanoic acid I've already written. Initial moles of propan-1-ol, 0.08. So let's put that in up here, 0.080. I can go back and see that in my pre-equilibrium mixture, look at the question, there's 0.111 moles of water. I'm given that answer. There's no ester to start with. Okay, and now I just use my changes. So it's all 1 to 1 to 1 in the equation. So I must have used 0.0618 moles of propanol. I must have made 0.0618 moles of water, and I must have made an extra 0.0618 moles of water. So now I just do my calculations. So moles of propan-1-ol at equilibrium is, I can put it down here just to show my working, 0.080 minus 0.0618, which gives me 0.0182 moles of the ester has just got to be that value of 0.0618. I can fill that in straight away. Moles of water has got to be 0.111 plus 0.0618. So 0.111 plus 0.0618 gives me 0.1728. Okay, so let's just go to the mark scheme and have a look at the values they're looking for. So now we see, calculation of equilibrium moles is 0.0182, 1 mark there, 1 mark there, and 1 mark there. Okay, so write the expression for the equilibrium constant. This should be easy, although it's surprising how many people make mistakes. Because these are liquids, they're not in aqueous solution, I have to include the concentration of water in there. Okay, so you only ignore the water if everything else is aqueous. So Kc equals concentration of products, just be careful copying it down. CH2, CH2, CH3, multiplied by concentration of water, divided by the ethanoic acid concentration, and the propan-1-ol concentration. It would probably be better really, I suppose, to put in state symbols, but usually you can get away without them. But you must have square brackets because that's the sign for concentration. Explain why it's possible in this case to calculate Kc using equilibrium amounts in moles rather than equilibrium concentrations. Well, have a look here. Concentration is moles divided by the volume. The total volume is going to be a constant. And you can see that because there's 2 concentrations on the top and 2 concentrations on the bottom, the total volume is just going to cancel. That's always the case when you've got the same number of moles on either side of the equation. So say same number of moles on each side of the equation. So total volume cancels in the expression. So calculating Kc value, now that's pretty easy because we've just had all our numbers, we've just written them all down, so we just substitute them in. So Kc, have our equation. The moles of ester, if we go back, was 0.0618. Our moles of water is 0.1728 divided by our moles of propan-1-ol 0.0182 and our moles of acid, which we had a bit earlier, which was 0.0432. Okay, so just go back and carefully check that you put the right values in there. So 0.0618 times 0.1728 divided by 0.0432 divided by 0.0182 gives me a long number. And generally 3SF is a good bet. So my least accurate value so far that I've quoted are 3SF, so I'm going to go for 3SF. 13.6, and there's no units because moles per dm cubed times moles per dm cubed divided by moles per dm cubed divided by moles per dm cubed, the units will cancel. Okay, so we get 1 mark for calculating the value and 1 for giving it to a sensible number of SF, 2 or 3. Okay, pink colour of phenolphthalein fading after the endpoint. This happens a lot actually. You have to be careful whenever you do an acid-base titration with phenolphthalein because once you reach the endpoint, if the endpoint is pink, it will fade because in acid, phenolphthalein is colourless, and of course in air there's a bit of carbon dioxide, and so over time carbon dioxide dissolves in whatever solution you've got, and therefore your solution becomes slightly acidic, and so the phenolphthalein turns colourless. So really straightforward answer, CO2 from air, so this could apply to lots of different titrations, dissolves in the solution, making it acidic. Okay, and 1 mark is for identifying a reason, so the CO2, and then second mark is for saying if it's going colourless, then it must be acidic. Explain what you could do to confirm that 1 week is sufficient time for the mixture to reach equilibrium. Well, if you left it for longer and you got the same values for the titer and for the Kc, then you would know that a week was long enough, that the equilibrium had been reached. So leave for longer than a week and compare values, compare titer. If titer unchanged, equilibrium had been reached in a week. If titer unchanged, 1 week was long enough. Again, 2 marks, you have to think about what you're saying really. So 1 is for what you do, second one is for explaining what you're looking for. Okay, student repeated the experiment, left water mixture in a water bath until equilibrium was reached. Describe the effect on this student's value for Kc. Okay, so Kc, you know the equilibrium constant isn't affected by any conditions apart from temperature. So temperature does affect it, and we're told the delta H for the reaction, so we should be using that. It's an endothermic forwards reaction. Okay, so 40 degrees C, it's warmer than room temperature. So as you increase the temperature, the equilibrium shifts to the right. So forwards reaction is endothermic. So higher temperature shifts equilibrium to the right. So now if you look at your values, you're going to have higher concentrations of the products. They were on the top of the Kc expression. Smaller values for the reactants, they were on the bottom of the Kc expression. So overall Kc is going to be larger. So therefore Kc is larger. Okay, so 1 mark for each.